Tonight, we begin a journey into an idea that seems deceptively simple, almost harmless at first glance, yet quietly undermines everything we think we understand about reality. It is a single number. Taught in classrooms, printed in textbooks, and repeated so often that it risks becoming invisible through familiarity. The speed of light. Not merely a measure of how fast something moves, but a boundary woven into the structure of the universe itself. To truly understand what this number represents is to discover that time does not flow the same for everyone, that space is not rigid, and that reality itself bends to preserve a cosmic rule that cannot be broken. For most of human history, the idea that light might have a speed at all would have sounded strange. Light seemed to simply be there. You opened your eyes, and the world appeared instantly. You lit a torch, and the darkness vanished without delay. When lightning tore across the sky, the flash arrived immediately, while the thunder rolled in later. To the ancient mind, the conclusion felt obvious. Sound takes time. Light does not. It arrives the moment it is born. This assumption made sense because human experience offered no reason to doubt it. Everyday distances are tiny compared to the scale at which light's motion becomes noticeable. Over a few meters, or even a few kilometers, lights travel. Time is so small that it slips entirely beneath human perception. For centuries, no experiment could challenge this intuition. And so the idea of instantaneous light quietly hardened into unquestioned truth. One of the earliest thinkers to challenge this belief was the Greek philosopher Empedocles, who lived in the 5th century BCE. He proposed that light was something that moved through space, and therefore must take time to travel. It was a remarkably modern idea, but it found little support. His contemporary Aristotle rejected it outright, arguing that light did not propagate like a physical object, but instead appeared instantaneously. Because Aristotle's authority dominated Western thought for more than 2,000 years, his view prevailed. Once Aristotle had spoken, the question seemed settled. Light was instantaneous. End of discussion. Elsewhere in the world, however, the idea refused to die completely. In the Islamic Golden Age, the scholar Ibn al-Haytham, known in the West as al-Hazm, revisited the nature of light in his monumental book of Optics, written around 1021. He argued that light travels from objects to the eye and does so at finite speed, behaving differently in different materials. This was a profound insight, far ahead of its time. But insight alone was not enough. Without a way to measure light's motion, these ideas remained philosophical speculation rather than established fact. The first serious attempt to turn speculation into measurement came in the 17th century with Galileo Galilei. Galileo understood that if light took time to travel, then in principle that time could be measured. In his book Two New Sciences, published in 1638, he described an experiment as simple as it was ambitious. Two observers would stand on distant hilltops, each holding a lantern with a shutter. The first observer would open their lantern. The moment the second observer saw the flash, they would open theirs. By measuring the delay between opening the first lantern and seeing the return flash, Galileo hoped to determine how long light took to make the round trip. Galileo tried this experiment over distances of less than a mile. He detected no delay at all. From this, he drew the only conclusion he reasonably could with the tools available to him. If light was not instantaneous, then it was at least extraordinarily fast. What Galileo could not know was just how hopelessly mismatched the experiment was to the phenomenon he was trying to observe. Light travels 1 mile in roughly 5 microseconds, 5 millionths of a second. Human reaction time, by contrast, is around 200,000 microseconds. The delay Galileo hoped to measure was about 40,000 times smaller than the uncertainty introduced by human reflexes. It was like trying to weigh a grain of sand with a bathroom scale. The failure was not conceptual. It was technological. The experiment simply could not succeed. Others repeated Galileo's approach and obtained the same null result. Measuring the speed of light would require distances far greater than anything available on Earth. It would require the sky itself to become part of the laboratory. That breakthrough came from an unexpected place, not from the behavior of light on Earth, but from the regular dance of moons around a distant planet. In the 1670s, a Danish astronomer named Ole Romer was working at the Paris Observatory under Giovanni Cassini. Romer's task was to create accurate tables predicting the eclipses of Io, one of Jupiter's moons, as it passed behind the planet. These eclipses occurred with clock-like regularity and were invaluable for navigation. As Romer compiled observations over months and years, he noticed something unsettling. The eclipses did not always occur exactly when predicted. When Earth was moving toward Jupiter in its orbit, the eclipses appeared slightly early. When Earth was moving away, they appeared slightly late. Over the course of a year, these small discrepancies accumulated into a difference of several minutes. Romer realized that the eclipses themselves were not changing. What was changing was the time it took for light to reach Earth. When Earth was closer to Jupiter, the light had less distance to travel. When Earth was farther away, the light had farther to go. The moon disappeared behind Jupiter at the same moment every time, but observers on Earth received news of that event sooner or later depending on where Earth happened to be in its orbit. This realization was revolutionary. It meant that even light, moving unimaginably fast, required time to cross space. Romer went further. In 1676, he predicted that a specific upcoming eclipse of Io would occur about 10 minutes later than traditional tables suggested. If he was wrong, his idea would collapse. If he was right, he would prove that light had a finite speed. When the predicted date arrived, astronomers watched carefully. The eclipse occurred exactly when Romer said it would. Light did not arrive instantly. It raced across space, but it took time. Romer estimated that light took about 22 minutes to cross the diameter of Earth's orbit, corresponding to a speed of roughly 140,000 miles per second. The value was not precise by modern standards, but the conclusion was undeniable. Aristotle had been wrong. Light had a speed. Over the next century, this idea was confirmed and refined. Astronomers like James Bradley discovered stellar aberration, a subtle shift in the apparent positions of stars caused by Earth's motion through space. The effect could only be explained if light took time to reach us. By measuring this shift and knowing Earth's orbital speed, Bradley calculated a value for the speed of light astonishingly close to the modern one. By the 19th century, scientists turned their attention back to Earth, determined to measure the speed of light in the laboratory. Ingenious experiments using rotating toothed wheels and mirrors, developed by physicists like Hippolyte Fizeau and Léon Foucault, finally succeeded where Galileo had failed. Light speed was measured over distances of a few miles with remarkable precision. For the first time, the cosmic was brought down to human scale. Yet as the measurements grew more accurate, a deeper mystery emerged. Light always seemed to travel at the same speed. No matter how carefully scientists measured, no matter the direction, no matter Earth's motion through space, the result never changed. This constancy would eventually force physics into a reckoning far more radical than anyone anticipated. By the end of the 19th century, the speed of light was no longer just a number. It was a stubborn fact, refusing to behave like any other speed in nature. And as the 20th century approached, it became clear that understanding this single number would require rewriting the rules of time, space, and reality itself. As measurements of light speed became more precise, physicists expected the mystery to fade. Instead, it deepened. According to everyday intuition, speeds should add together. If you walk forward on a moving train, someone standing on the platform sees your speed as the train's speed plus your walking speed. This rule worked perfectly for balls, arrows, and cannonballs. There was no reason to think light should be any different. And yet, every experiment stubbornly showed the same result. Light did not care how fast its source was moving. It did not care how fast the observer was moving. It always traveled at the same speed. This created a serious problem for 19th century physics. At the time, light was understood as a wave, and all known waves required a medium to travel through. Sound needs air. Ocean waves need water. So physicists proposed a medium for light, an invisible substance filling all of space, called the luminiferous ether. Light waves, they believed, rippled through this ether. The way sound ripples through air. If the ether existed, then Earth must be moving through it as our planet orbited the Sun. And if Earth was moving through the ether, then light traveling in the direction of Earth's motion should move at a slightly different speed than light traveling perpendicular to it. The difference would be tiny, but with sufficiently sensitive equipment. It should be detectable. Measuring that difference became one of the most important experimental goals of the era. The man who took on this challenge with unmatched precision was Albert Michelson, an American physicist obsessed with measurement accuracy. Michelson developed an instrument called an interferometer, capable of detecting incredibly small differences in the time it took light to travel along different paths. In 1887, working with Edward Morley, he set out to measure Earth's motion through the ether once and for all. The experiment was elegant. A beam of light was split into two perpendicular paths, bounced off mirrors, and recombined. If one beam traveled slightly faster than the other because of Earth's motion through the ether, the recombined light would show a shift in its interference pattern. Michelson and Morley expected to see that shift. Instead, they saw almost nothing. They rotated the apparatus. They repeated the experiment at different times of day and different times of year. The result never changed. Light traveled at the same speed in every direction. Earth's motion made no detectable difference. Michelson later described the outcome plainly. The result was decidedly negative. This failure became one of the most important results in the history of science. The ether, which had seemed so necessary, appeared to have no effect on light at all. And if the ether did not exist, or could not be detected even in principle, then the entire framework used to understand light waves was in trouble. By the turn of the 20th century, physics stood at an uncomfortable crossroads. Experiments had shown two things with increasing certainty. First, the laws of physics seemed to be the same in all uniformly moving frames of reference. Second, the speed of light was constant, independent of the motion of the source or the observer. Taken separately, each idea seemed reasonable. Taken together, they were explosive. In 1905, a 26-year-old patent clerk in Bern, Switzerland, confronted this contradiction head-on. Albert Einstein was not working in a university. He had no laboratory. He spent his days examining patent applications. But in his spare time, he thought deeply about the foundations of physics, guided by a simple question that had troubled him since his teenage years: what would it look like to chase a beam of light? According to Newtonian physics, if you could run fast enough to keep pace with a light wave, you should see it frozen in space, a stationary ripple of electromagnetic fields. But Maxwell's equations, which governed electromagnetism, allowed no such thing. They demanded that light always move at the same speed. A frozen light wave was forbidden. Einstein realized that the problem was not with the equations. It was with the assumptions underlying space and time themselves. In his special theory of relativity, published in 1905, Einstein proposed two postulates that would change our understanding of reality forever. The first was the principle of relativity: the laws of physics are the same in all inertial reference frames. There is no absolute state of rest. No experiment performed inside a smoothly moving system can tell you whether you are moving or standing still. The second postulate was even more radical: the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This was not a hypothesis to be tested later. It was a statement forced upon physics by experiment. Michelson and Morley had already shown that light speed does not vary with direction or motion. Einstein simply accepted this fact and followed it to its logical conclusion. Those conclusions were shocking. If the speed of light is the same for everyone, then time and space cannot be absolute. They must adjust themselves so that light speed remains constant. Time must slow down for moving objects. Space must contract. Events that appear simultaneous to one observer may not be simultaneous to another. At first glance, this seems impossible. Time slowing down sounds like an illusion, a trick of perception. But relativity insists it is real. A moving clock does not merely appear to run slow. It actually runs slow. Time itself passes more slowly for objects in motion. To see why, imagine a simple clock made of light bouncing between two mirrors. Each round trip of the light marks one tick. If the clock is stationary relative to you, the light moves straight up and down. But if the clock is moving sideways at high speed, the light traces a diagonal path. That path is longer, and since light speed cannot change, the journey takes more time. Each tick lasts longer. The clock runs slow. This is not a special property of light clocks. Any process that measures time behaves the same way. Chemical reactions slow. Atomic vibrations slow. Biological aging slows. Motion changes the flow of time itself. As speed increases, the effect becomes dramatic. At everyday speeds, the difference is negligible. At speeds approaching the speed of light, it becomes overwhelming. At 90% of light speed, time passes less than half as fast. At 99%, years for a stationary observer collapse into days for the traveler. Alongside time dilation comes length contraction. Objects moving relative to you become shorter in the direction of motion. This is not a visual illusion. The object genuinely occupies less space. A spaceship traveling near light speed would measure the distance to its destination as far shorter than what an observer at rest would measure. These effects are two sides of the same coin. They ensure that all observers, no matter how fast they are moving, measure the same speed for light. Reality bends to protect that rule. Perhaps the strangest consequence of all is the relativity of simultaneity. In everyday life, we assume that now is universal. That events either happen at the same time or they do not. Relativity shatters this assumption. Two events that are simultaneous for one observer may occur at different times for another observer moving relative to the first. There is no single cosmic present. Different observers carry their own versions of now through the universe. This is not a limitation of measurement. It is how time itself is structured. By accepting the speed of light as absolute, Einstein revealed a universe far stranger than anyone had imagined. Space and time were no longer passive stages on which events unfolded. They were active participants, stretching and warping to preserve a single, inviolable speed limit. And this was only the beginning. Once the flexibility of time and space is accepted, a cascade of consequences follows, each stranger than the last, yet all bound together by strict mathematical necessity. What initially feels like paradox gradually reveals itself as a coherent, if deeply counterintuitive, picture of reality. The universe does not contradict itself. It simply refuses to conform to human intuition shaped by slow speeds and small distances. One of the most famous illustrations of relativistic effects is known as the twin paradox. Imagine two identical twins. One remains on Earth, living an ordinary life. The other boards a spacecraft capable of traveling at speeds close to that of light and journeys to a distant star before returning home. From Earth's perspective, the story seems straightforward. The star is, say, 10 light-years away. Traveling at 90% of the speed of light, the outbound trip takes a little over 11 years, and the return trip takes another 11. More than 20 years pass on Earth. But from the traveling twin's perspective, the situation is very different. Because of length contraction, the distance to the star is not 10 light-years. At that speed, space itself shrinks along the direction of travel. The star is only a few light-years away. The journey takes far less time. When the spacecraft finally returns to Earth, the traveling twin has aged only about 9 or 10 years, while the twin who stayed behind has aged more than 20. They began the same age. They reunite at different ages. One twin is now significantly older than the other. At first glance, this seems impossible. Motion is relative, after all. Why can't the traveling twin claim that Earth was the one moving? Why doesn't the Earthbound twin end up younger instead? The resolution lies in the fact that the situation is not symmetric. The traveling twin must accelerate to leave Earth, accelerate again to turn around, and decelerate to return. The Earthbound twin remains in a single inertial frame the entire time. Acceleration breaks the symmetry, and the result is unambiguous. The traveling twin experiences less time. This is not science fiction. It is not a thought experiment that lives only on paper. Versions of the twin paradox have been tested directly using atomic clocks flown around the world on airplanes and satellites. The clocks that move return measurably out of sync with those that stay behind. The predictions of relativity match the results precisely. Time itself has passed differently for different observers. Another profound consequence of the speed of light is the existence of an absolute speed limit. Nothing with mass can ever reach the speed of light. As an object accelerates, its energy increases. But energy and mass are intimately connected. The faster an object moves, the more resistant it becomes to further acceleration. Each additional increase in speed requires more energy than the last. As the object approaches the speed of light, the required energy grows without bound. To reach the speed of light would require infinite energy, an impossibility. This is why massive objects can approach light speed but never attain it. The speed of light is not merely a practical limitation of engines or fuels. It is a fundamental boundary built into spacetime itself. Light, by contrast, behaves in the opposite way. Photons have no mass. Because of this, they cannot travel at any speed other than the speed of light. They are born moving at that speed and never slow down. Light does not choose its speed. Physics gives it no alternative. This realization leads to a subtle but crucial insight. The speed of light is not just about light. It is the speed at which cause and effect propagate through the universe. It is the maximum speed at which information, influence, or change can travel. In this sense, the speed of light is more accurately described as the speed of causality. To visualize this, physicists use a concept called the light cone. Imagine an event occurring at a particular place in time. From that event, light spreads outward in all directions, forming a cone shape in spacetime diagrams where time points upward and space spreads outward horizontally. Everything inside the future light cone consists of events that can be influenced by the original event. Everything inside the past light cone consists of events that could have influenced it. But outside these cones lies a vast region called elsewhere. Events in this region are fundamentally disconnected. No signal, no force, no influence can travel between them without exceeding the speed of light. For these events, even the order in which they occur can depend on the observer. One observer may see event A happen before event B. Another observer, moving at a different speed, may see B happen before A. There is no contradiction, because neither event can cause the other. This structure explains why faster-than-light travel would create catastrophic problems. If information could travel faster than light, it would be possible, in some reference frames, for effects to precede their causes. Messages could arrive before they were sent. Paradoxes would multiply. The universe seems designed to prevent this. The speed of light protects the logical consistency of reality. Over the past century, these predictions have been tested with extraordinary precision. One of the most striking confirmations comes from particles called muons. Muons are unstable subatomic particles created when cosmic rays strike Earth's atmosphere. At rest, they decay in just a few microseconds. Even traveling at nearly the speed of light, they should not survive long enough to reach the ground from high in the atmosphere. And yet they do. From Earth's perspective, the explanation is time dilation. The muons are moving so fast that their internal clocks run slow. Their brief lifetimes stretch long enough for them to reach detectors on the surface. From the muons' perspective, the explanation is length contraction. The atmosphere they must cross is compressed into a much shorter distance. Both explanations are correct, each within its own reference frame. Nature is consistent, even when our intuitions are not. Relativity also plays a role in everyday technology. The Global Positioning System, GPS, depends critically on relativistic corrections. GPS satellites carry atomic clocks that tick with extraordinary precision. Because these satellites are moving relative to Earth and sit in weaker gravitational fields, their clocks run at different rates than clocks on the ground. If these differences were not corrected using Einstein's equations, GPS errors would accumulate rapidly, making the system useless within minutes. Every time a phone guides you through a city, relativity is quietly at work. As strange as all of this already seems, it leads to an even deeper realization. Space and time are not separate entities. They are interwoven into a single, four-dimensional fabric called spacetime. Events are not just located somewhere in space. They are located somewhere in spacetime. Motion through space affects motion through time, and vice versa. This union was formalized by Hermann Minkowski, who showed that Einstein's ideas could be expressed elegantly using four-dimensional geometry. Space by itself and time by itself, he said, are doomed to fade away into mere shadows. Only their union preserves an independent reality. Once spacetime becomes the stage, gravity itself takes on a new meaning. And with that insight, Einstein was led beyond special relativity toward an even more radical theory, one that would reveal how mass and energy curve spacetime itself. The story of the speed of light does not end with motion and clocks. It reaches into gravity, cosmology, and the ultimate limits of what we can know about the universe. And as we will see next, it also confronts us with a sobering truth. No matter how advanced our technology becomes, the cosmos may forever remain larger than our reach. When Einstein extended his thinking beyond uniform motion, he arrived at a realization that would reshape our understanding of gravity itself. In special relativity, motion alters time and space. In general relativity, mass and energy do the same. Gravity, in this view, is not a force pulling objects through space, but the curvature of spacetime caused by mass and energy. And once again, the speed of light sits at the center of the story, quietly enforcing the rules. In everyday life, gravity feels simple. Objects fall. Planets orbit. For centuries, Newton's law of universal gravitation described these motions with astonishing accuracy. But Newton's theory carried an uncomfortable implication. Gravitational influence seemed to act instantaneously across vast distances. If the sun were to disappear, Earth would, according to Newton, instantly feel the change. This clashed with The growing realization that nothing, not even light, could travel infinitely fast. General relativity resolved this tension. Changes in gravity propagate at the speed of light. If the sun vanished, Earth would continue orbiting for about 8 minutes, the time it takes light to travel from the sun to Earth. Only then would the gravitational effect reach us. Gravity obeys the same cosmic speed limit as everything else. This insight led to one of the most dramatic predictions in physics: light itself should be affected by gravity. If spacetime is curved by mass, then light traveling through that curved spacetime should follow a bent path. During a total solar eclipse in 1919, astronomers measured the apparent positions of stars near the sun's edge. The starlight was bent exactly as Einstein predicted. Overnight, Einstein became a global figure, and the speed of light once again proved to be the thread tying theory to reality. General relativity deepens the strangeness of time. Not only does motion slow clocks, but gravity does as well. A clock closer to a massive object ticks more slowly than one farther away. Time flows at different rates at different heights in a gravitational field. This effect has been measured repeatedly, from laboratory towers to satellites in orbit. Time is not uniform. It pools and stretches under the influence of mass. With this understanding, the universe itself becomes a laboratory for the speed of light. The vast distances of space turn light into a time machine. When we look at the moon, we see it as it was just over a second ago. When we look at the sun, we see it as it was 8 minutes in the past. Distant galaxies appear as they were millions or billions of years ago. Astronomy is not just the study of space. It is the study of history. The finite speed of light defines the observable universe. The universe is about 13.8 billion years old, which means light has had only that much time to reach us. There is a horizon beyond which we cannot see, not because nothing exists there, but because light from those regions has not yet arrived. This horizon is not fixed. As time passes, we see more of the universe, but the expansion of space complicates the picture. Space itself is expanding, carrying galaxies away from each other. Some distant galaxies are receding from us faster than the speed of light, not because they are moving through space at impossible speeds, but because space itself is stretching. This does not violate relativity. The speed limit applies to motion through spacetime, not to the expansion of spacetime itself. Light emitted from beyond a certain distance will never reach us, no matter how long we wait. Those regions are forever causally disconnected from our own. This cosmic speed limit also places hard constraints on exploration. Even traveling at speeds close to light, journeys to nearby stars would take years or decades as measured from Earth. Communication delays would stretch into years. A conversation with a civilization around another star would unfold over generations. The dream of a galaxy-spanning civilization collides head-on with the reality imposed by the speed of light. Naturally, this has inspired speculation about ways around the limit. Quantum entanglement, often misunderstood, does not allow faster-than-light communication. While entangled particles exhibit instant correlations, those correlations cannot be controlled or used to transmit information. They preserve the cosmic speed limit, not violate it. Other ideas, like hypothetical faster-than-light particles or exotic spacetime geometries, face severe theoretical obstacles. Even concepts such as warp drives, which involve bending spacetime rather than moving through it, require forms of energy that may not exist in nature. The equations permit strange possibilities, but whether the universe allows them remains an open question. What is clear is that the speed of light is not an arbitrary number. It is a structural feature of reality. It governs how events influence one another. It defines what can be known, what can be reached, and what must forever remain beyond our grasp. And yet, this limit is not merely restrictive. It gives the universe coherence. It ensures that cause precedes effect. It weaves time and space into a consistent whole. Without it, reality would unravel into paradox. In the end, the speed of light is not just about how fast light moves. It is about how the universe is allowed to work. It tells us that reality has a shape, a structure, and boundaries that no amount of ingenuity can simply wish away. As we push our understanding further, the question is no longer whether the speed of light breaks our intuition. It clearly does. The deeper question is what it reveals about our place in a universe governed by laws that are beautiful, unforgiving, and profoundly strange. At this point in the story, it becomes clear that the speed of light is not merely a scientific curiosity or a technical parameter in equations. It is a lens through which the universe reveals its deepest rules. And as our understanding matures, a more unsettling realization emerges: the speed of light does not just limit motion and communication. It limits knowledge itself. Because information cannot travel faster than light, there are events in the universe that are, in principle, unknowable to us. No matter how advanced our instruments become, no matter how long we wait, some regions of spacetime will remain forever beyond observational reach. This is not a failure of technology. It is a fundamental feature of reality. This becomes especially clear when we consider cosmology. The universe is not static. It is expanding, and that expansion is accelerating. As a result, there exists a cosmic event horizon, similar in spirit to the event horizon of a black hole. Beyond this horizon, galaxies are receding so rapidly that their light will never reach us. Even if those galaxies emit light forever, the expansion of space will stretch and carry that light away faster than it can travel toward us. This means the observable universe is not just a snapshot of everything that exists. It is a shrinking sample of a much larger whole. Over immense spans of time, more and more galaxies will slip beyond our cosmic horizon, fading from view. Future astronomers, billions of years from now, may see a far lonelier universe than we do today, with distant galaxies erased by the relentless expansion of space. Black holes push this idea to an even more extreme limit. At the boundary of a black hole, known as the event horizon, the escape velocity equals the speed of light. Beyond this boundary, all paths through spacetime lead inward. Light itself cannot escape. Information carried by matter or radiation that crosses the event horizon is cut off from the rest of the universe forever. To an outside observer, objects falling toward a black hole appear to slow down and freeze near the event horizon, their light stretched and reddened as it struggles against gravity. From the falling object's own perspective, however, nothing special happens at the horizon. It crosses smoothly and continues inward. This difference in perspective once again highlights the strange, observer-dependent nature of time enforced by the speed of light. Black holes raise deep questions about information. If information cannot escape from beyond the event horizon, what happens to it? Does it vanish? Is it stored somehow on the surface of the horizon? These questions touch the foundations of physics, where relativity, quantum mechanics, and the speed of light intersect in ways we do not yet fully understand. Quantum theory introduces its own tensions. In the quantum world, particles behave in ways that seem to defy classical notions of locality. Entangled particles share correlations that appear instantaneous, regardless of distance. This has led to the seductive but incorrect idea that quantum mechanics allows faster-than-light communication. Experiments have shown, again and again, that while quantum correlations are real, they cannot be used to send information faster than light. The outcomes are fundamentally random. You cannot choose what message to encode in an entangled particle. The universe preserves its speed limit, even at the quantum level. This preservation appears almost intentional, as if the fabric of reality is carefully stitched to avoid causal paradoxes. Every time physics flirts with the possibility of breaking the light-speed barrier, deeper principles step in to prevent it. As our theories advance, the speed of light increasingly looks less like the speed of a particular phenomenon and more like a conversion factor between space and time. In natural units used by physicists, the speed of light is often set equal to 1. In this framework, space and time are measured in the same units, emphasizing their deep connection. Distance can be expressed as time, and time as distance. Light simply traces the structure of spacetime itself. From this perspective, asking why the speed of light has the value it does becomes a subtle question. It is not so much about why light moves at that speed, but why spacetime has the geometry it does. The number we call the speed of light reflects how tightly space and time are interwoven in our universe. This shift in thinking also changes how we see ourselves. We are not just beings moving through space. We are beings moving through spacetime, always traveling forward in time at the maximum possible rate. When we move faster through space, we move more slowly through time. The speed of light sets the balance between these two motions. Even in the most abstract corners of theoretical physics, the speed of light remains central. Attempts to unify gravity with quantum mechanics, whether through string theory, loop quantum gravity, or other approaches, must all respect the light speed limit at large scales. Any successful theory of everything must explain why this limit exists and why it is so fundamental. In this sense, the speed of light is a kind of guardian of consistency. It ensures that the universe remains intelligible, that causes precede effects, and that reality does not collapse into contradiction. It may frustrate our dreams of instantaneous travel and communication, but it also makes a coherent universe possible. As we approach the end of this exploration, one final idea comes into focus. The speed of light does not merely break our understanding of reality. It reveals that our everyday understanding was never complete to begin with. What feels solid and absolute, time, space, simultaneity, turns out to be flexible, relational, and deeply interconnected. And in recognizing this, we are reminded of something humbling. The universe is not obligated to align with human intuition. It operates according to principles that are elegant, precise, and often profoundly strange. The speed of light is one of those principles, quietly shaping everything from the ticking of clocks to the fate of galaxies. To understand it is not just to learn a fact about physics. It is to glimpse the hidden architecture of reality itself. When we step back and look at the full arc of this story, a final, quieter implication begins to emerge. The speed of light does not only define the limits of physics. It shapes the way existence itself unfolds. Every moment you experience, every memory you form, every thought you finish thinking, is constrained by this silent rule written into spacetime. You never perceive the present directly. What you call now is always slightly in the past. The light reflecting off the screen you are reading, the faces you recognize, the world outside your window, all take time to reach your eyes. That delay is tiny, but it is never zero. You live in a universe where immediacy is an illusion, and perception is always historical. At human scales, this delay is meaningless. But at cosmic scales, it becomes everything. Entire civilizations could rise and fall on distant planets without our ever knowing. Even if intelligent beings were watching Earth from far away, what they would see is not us as we are, but Earth as it once was. The farther away the observer, the deeper into our past they would be looking. This leads to a strange but unavoidable conclusion. There is no single, shared present for the universe as a whole. Each observer carries their own slice of spacetime, their own definition of now, shaped by motion, gravity, and distance. The universe does not advance in lockstep. It unfolds as a mosaic of overlapping timelines, stitched together by light. From this perspective, the idea of absolute simultaneity dissolves completely. Two events happening at the same time only have meaning relative to a specific observer. Change the observer's motion, and the temporal order of distant events can change as well. The speed of light ensures that no contradiction arises. But it also guarantees that reality is deeply relational. This relational nature challenges something deeply human, the desire for certainty and universality. We want the universe to have a single clock, a single flow of time that everyone shares. Relativity tells us that such a clock does not exist. Time is local. It belongs to paths through spacetime, not to the universe as a whole. Even causality, which feels unshakable, turns out to be carefully guarded rather than absolute. The speed of light draws a boundary around what can influence what. Inside that boundary, cause and effect are preserved. Outside it, the universe refuses to assign a definite order at all. It is not that causality breaks down, it is that it is not defined where influence is impossible. This realization forces us to rethink the notion of reality as something fully determined and globally ordered. Instead, reality is layered. Some events are firmly connected by cause and effect. Others coexist without any meaningful relationship, their order depending on perspective. The speed of light is what keeps these layers from collapsing into chaos. There is a subtle beauty in this restraint. The universe allows complexity, change, and structure, but only within carefully drawn limits. By capping the speed of information, it prevents runaway paradoxes. It gives time room to exist as something more than a universal metronome. It gives space the freedom to stretch, curve, and expand. Even our search for ultimate truth is shaped by this limit. Scientific knowledge relies on observation, and observation relies on signals traveling at or below the speed of light. There are questions we can ask but never answer experimentally because the relevant information can never reach us. This is not pessimism. It is an honest boundary between what is knowable and what is not. And yet, within those boundaries, the universe is astonishingly generous. From faint ripples in spacetime to echoes of the Big Bang itself, light has carried to us a detailed story of cosmic history. The same limit that hides parts of reality also reveals others with exquisite clarity. The speed of light does not just constrain discovery, it makes discovery possible. Perhaps this is the most profound lesson of all. Limits are not merely restrictions. They are structures. Without them, there is no coherence, no narrative, no stable world in which anything meaningful can occur. The speed of light is one such structure, shaping the universe into something intelligible, rather than arbitrary. As we approach the final stretch of this exploration, what remains is not a sense of frustration, but one of perspective. We are creatures embedded in spacetime, subject to its rules, yet capable of understanding them. We cannot outrun light, but we can grasp why it cannot be outrun. We cannot see beyond certain horizons, but we can understand why those horizons exist. The speed of light stands as a reminder that reality is not built for convenience. It is built for consistency. And within that consistency lies a strange and quiet elegance. One that continues to challenge, humble, and inspire anyone who dares to look deeply enough. There is a final layer to this story that often goes unnoticed, because it is less about equations and experiments, and more about meaning. Once we accept that the speed of light shapes time, space, causality, and knowledge itself, we are forced to confront how radically different the universe is from the one our instincts prepared us for. And in doing so, we are also forced to reconsider what it means to exist within such a universe. Human intuition evolved in a world where speeds are slow, distances are short, and gravity is gentle. In that environment, time feels universal, space feels solid, and cause and effect feel immediate. Relativity reveals that these impressions are not wrong, but incomplete. They are approximations that work only because the speed of light is so large compared to the speeds of everyday life. We live in the shadow of a deeper reality, buffered from its strangeness by scale. This buffering is not accidental. If the speed of light were much slower, everyday life would be unrecognizable. Conversations would be delayed. Simple actions would unfold out of order depending on perspective. Cause and effect would feel unreliable. Conscious experience itself might become fragmented. The high value of the speed of light is what allows a stable, shared human experience to exist at all. In this sense, the speed of light is not just a physical constant. It is a condition for complexity. It allows large structures to form and persist. It gives stars time to burn, planets time to cool, and life time to evolve. If information propagated too quickly or too slowly, the balance required for structure might never arise. This idea appears again when we consider the early universe. Shortly after the Big Bang, the universe was hot, dense, and rapidly expanding. Regions of space that are now widely separated were once much closer together. Yet even then, the speed of light limited how quickly different regions could exchange information. This raises the horizon problem: why does the universe look so uniform in temperature and structure, even in regions that should never have been in causal contact? Modern cosmology addresses this with the theory of inflation, a brief period of extremely rapid expansion. Early in cosmic history, inflation does not violate the speed of light because it involves the expansion of space itself, not motion through space. Once again, the speed of light remains untouched, quietly constraining what is possible while allowing the universe to become what it is. As our theories push toward the Planck scale, where quantum mechanics and gravity intersect, the role of the speed of light becomes even more enigmatic. At these extremes, spacetime itself may become granular or emergent, composed of more fundamental elements. Some theories suggest that space and time are not fundamental at all, but arise from deeper informational or relational structures. If this is true, then the speed of light may not be a property of particles moving through spacetime, but a property of how spacetime itself emerges. It may represent the maximum rate at which the underlying structure of reality can update or reconfigure. In this view, the speed of light is not just a limit within the universe. It is a limit of the universe. This perspective reframes an old question. Instead of asking why nothing can travel faster than light, we ask why reality has a maximum speed at all. Why is there a limit? Why not infinite speed, or no speed? The existence of a limit suggests that reality is not arbitrary. It has an internal logic that resists contradiction. Philosophically, this challenges classical ideas of determinism and objectivity. If time is relative and simultaneity is not absolute, then the universe cannot be described from a single, privileged viewpoint. There is no view from nowhere. Every description is tied to a perspective. Truth becomes something that must be carefully translated between observers rather than assumed to be universally obvious. Yet this does not mean reality is subjective in a casual sense. The laws are the same for everyone. The speed of light is the same for everyone. What changes is how those laws are experienced. Objectivity survives, but it becomes more subtle. It is embedded in relationships, not absolutes. This relational objectivity has practical consequences. It teaches humility. It reminds us that no single observer, no single civilization, no single frame of reference has a complete picture of reality. Each perspective captures part of the truth. And the full structure emerges only when those perspectives are woven together through the language of physics. In a strange way, the speed of light enforces cooperation. It forces us to acknowledge limits, delays, and differences in perspective. It prevents domination by any single viewpoint. Even the universe itself does not get to have a global now. As this exploration draws closer to its conclusion, one idea stands out with increasing clarity. The speed of light is not an obstacle to understanding reality. It is the key to understanding why reality has the shape it does. It explains why time flows, why space stretches, why causality holds, and why the universe is intelligible at all. We began with a simple question: how fast does light travel? Along the way, that question dissolved into something far deeper. Light does not merely travel through reality. It defines reality's limits. And perhaps that is the most unsettling and inspiring truth of all. The universe is not boundless in every direction. It has edges, horizons, and constraints. Yet within those constraints, it unfolds with extraordinary richness. The speed of light does not diminish the universe. It gives it form. At the very end of this exploration, one final realization settles in, not as a dramatic revelation, but as a quiet shift in how everything fits together. The speed of light does not sit at the edge of physics like a boundary fence. It runs through the center of reality like a spine. Remove it, or change it, and the entire structure collapses into something unrecognizable. Consider what it means that the universe has a maximum speed. It means the universe unfolds, rather than simply exists all at once. Events must wait their turn to influence one another. Causes must travel before effects can appear. Reality is not a static block revealed instantly, it is a process, continuously updating, moment by moment, limited by how fast information can move. This turns existence itself into a kind of narrative. Every story requires order. Something happens, then something else follows. The speed of light is what enforces that order on the largest possible scale. Without it, the universe would lose its sense of sequence. History would blur. Prediction would become meaningless. Responsibility would have no anchor. In this sense, time is not just measured by clocks. Time is enforced by light. When you move through the world, you are always moving through spacetime at the same fundamental rate. If you remain still in space, you move fully through time. If you move quickly through space, you sacrifice some of that motion through time. The speed of light is the bookkeeping rule that keeps this balance exact. Nothing is wasted. Nothing is free. This balance explains why the universe feels stable. It also explains why it feels resistant to our attempts at shortcuts. Faster than light travel, backward time travel, instantaneous communication, all of these ideas fail not because we lack cleverness, but because they threaten the accounting system that keeps reality consistent. Every paradox you can imagine, messages sent to the past, effects without causes, contradictions looping endlessly, begins with violating the speed of light. And every known law of physics responds the same way, it refuses. What is remarkable is how often the universe had the opportunity to allow exceptions, and how consistently it chose not to. Quantum mechanics could have broken causality. It did not. Gravity could have acted instantaneously. It does not. Even spacetime expansion obeys the rule in its own way, stretching distances without letting information cheat. This consistency suggests that the speed of light is not a local rule patched into physics, but a global requirement. It is the universe insisting on being logically self-contained. From a human perspective, this can feel limiting. We imagine futures where distance no longer matters, where messages arrive instantly, where exploration is unconstrained. The speed of light reminds us that some dreams collide with the structure of reality itself. But it also reminds us of something else: meaning requires limits. A universe with no delay would be overwhelming. Everything would happen everywhere at once. There would be no patience, no anticipation, no discovery. Distance would have no meaning, and neither would journey. The finite speed of light gives separation value. It gives travel significance. It gives communication weight. When light finally reaches us from a distant star, it has crossed billions of kilometers and millions of years. That journey is part of the message. Without the delay, the information would be cheaper, thinner, less profound. The universe does not rush its stories. This perspective reframes our place in the cosmos. We are not spectators watching a completed reality. We are participants embedded in an unfolding one. We receive information as it becomes available, never all at once, never ahead of time. Knowledge arrives in layers, shaped by distance and motion and gravity. Even our most advanced theories respect this humility. They do not promise omniscience. They promise consistency. They promise that if we wait, observe carefully, and respect the limits, the universe will reveal itself, slowly, honestly, and without contradiction. And perhaps that is the final lesson hidden inside the speed of light. Reality is not designed to be instantly grasped. It is designed to be discovered. The universe does not shout its truths across infinite distances in no time at all. It whispers them, carried by light, arriving when they are allowed to arrive. Every insight we gain has waited its turn to reach us. In that waiting, meaning forms. So the speed of light does not break reality. It protects it. It guards the order of events, the flow of time, and the possibility of understanding. It draws the line that turns chaos into cosmos. And once you see that, the number itself, 299. 792,458 meters per second, no longer feels like a statistic. It feels like a signature. A quiet declaration written into spacetime, saying, this is how the universe stays whole. And even after all of this, after we have followed the speed of light from ancient philosophy to modern physics, from laboratory experiments to cosmic horizons, there is still one last turn in the road. It is the realization that understanding the speed of light changes not only how we see the universe, but how we see certainty itself. For most of history, knowledge was imagined as something absolute. If we measured carefully enough, reasoned clearly enough, we believed we could describe reality exactly as it is. The speed of light quietly dismantles that dream. Not by denying truth, but by reshaping it. Truth becomes something that depends on position, motion, and perspective, yet remains consistent when translated correctly. This is one of the most radical shifts in human thought. Reality is no longer a single picture viewed from nowhere. It is a structure revealed differently to different observers, all bound together by shared laws. The speed of light is what makes that translation between perspectives possible. Without it, there would be no stable way to relate one viewpoint to another. In this sense, physics becomes a language rather than a decree. It tells us how different descriptions connect, not which one is the correct one. Time dilation, length contraction, and relativity of simultaneity are not distortions. They are translations between equally valid experiences. This has an unexpected emotional consequence. It teaches us intellectual humility. No observer, no matter how advanced, ever sees the full picture. Every perspective is partial. Every measurement is local. Even the universe itself does not present a single global now. And yet, this humility does not weaken understanding. It strengthens it. By accepting limits, physics gains clarity. By respecting the speed of light, reality remains intelligible rather than contradictory. There is a parallel here with human experience. No person sees the whole truth of any moment. Everyone occupies a position in space and time, shaped by history, motion, and circumstance. Understanding emerges not from erasing those differences, but from recognizing and relating them. In an unexpected way, the universe's deepest rule mirrors something profoundly human. The speed of light also reframes progress. Advancement is not about eliminating delay, but about working within it. Telescopes do not make light arrive faster, they make us better at listening. Satellites do not cancel time dilation, they account for it. Science does not defeat the universe's limits, it collaborates with them. And that collaboration has been remarkably successful. From predicting eclipses to detecting gravitational waves. From mapping the cosmic microwave background to synchronizing global navigation systems, our understanding of the speed of light has allowed us to build technologies and theories that would have seemed miraculous just centuries ago. Yet for all this success, the speed of light remains stubbornly untouched. It has not shifted. It has not bent to convenience. It stands unchanged as experiments grow more precise and theories more ambitious. Other constants may someday be explained or derived from deeper principles. But even then, the speed of light will remain woven into the outcome. Perhaps that is why it inspires such fascination. It feels less like a discovered fact and more like a revealed constraint, as if the universe is saying, this is how coherence is preserved. And so we end where we began, with a number that looks ordinary on the page, but extraordinary in meaning. A speed that is not just fast, but final. Not just measured, but enforced. The speed of light does not ask whether we approve of its limits. It does not adjust to our ambitions. It simply holds the universe together, moment by moment, signal by signal, cause by cause. To understand it is to accept that reality is larger than intuition, deeper than immediacy, and more patient than desire. It is to accept that some doors remain closed, not out of cruelty, but out of necessity. And within those boundaries, the universe unfolds with stunning richness. This is why the speed of light matters. Not because it tells us how quickly light travels, but because it tells us what kind of universe we live in. A universe where time is flexible but ordered. Where space is dynamic but consistent. Where knowledge arrives, always on time, never early. Never late. A universe that does not rush, does not rewind, and does not contradict itself. A universe that waits for light to arrive. And if we listen carefully to that waiting, we begin to hear something deeper than physics alone. The speed of light is not just a rule about motion, it is a rule about restraint. It tells the universe how fast it is allowed to reveal itself. And it tells us how fast we are allowed to understand it. In a culture that celebrates immediacy, this is a quietly radical idea. We are used to thinking that faster is better, that delay is a flaw. To be engineered away. But the universe disagrees. It insists that delay is fundamental. That separation matters. That not everything should be accessible at once. Because light takes time. Mystery can exist without contradiction. Because signals are delayed, anticipation has meaning. Because information arrives gradually, learning is possible. The speed of light is what turns ignorance into curiosity rather than confusion. Imagine a universe where every event was instantly known everywhere. There would be no perspective, no discovery, no unfolding. Everything would collapse into a single, overwhelming moment. In such a universe, experience itself would lose structure. The finite speed of light prevents that collapse. It gives reality room to breathe. This also explains why the universe feels vast. Distance is not just space between objects, it is time between messages. When you look at the stars, you are not just seeing far away, you are seeing long ago. The sky is not a ceiling above us. It is a deep archive surrounding us in all directions. And you, standing beneath it, are not outside this system. You are part of it. Every thought you have is constrained by signals moving through neurons at finite speeds. Every memory is ordered by cause and effect. Your own sense of self is built on the same principle that governs galaxies and black holes. In that sense, the speed of light is not something out there. It runs through you. This realization closes the distance between cosmology and everyday life. The same rule that prevents faster-than-light travel also allows a conversation to make sense. The same limit that defines cosmic horizons also protects the sequence of your memories. The universe is not divided into the large and the small. It is unified by constraint. There is something deeply reassuring about this unity. It means that the laws shaping the most distant corners of existence are the same laws shaping the moment you are living right now. Nothing special has to be added to explain meaning, order, or continuity. They emerge naturally from the structure imposed by light's finite speed. And so, when we ask whether the speed of light breaks reality, the answer becomes clear. It breaks the illusion that reality should be simple, immediate, or centered on us. But it replaces that illusion with something far more powerful, a universe that is internally consistent, endlessly rich, and open to understanding. The speed of light does not block our view of reality. It defines the angle from which reality can be seen. It teaches us that to know the universe is to wait for it. To understand is to accept delay. To explore is to move within limits, not beyond them. And in doing so, it reveals a final, quiet truth. Reality is not fast. Reality is not slow. Reality moves at exactly the speed it needs to remain whole. That speed is the speed of light. At last, the story settles into stillness, not because there is nothing more to say, but because everything essential has already been placed. What remains is not explanation, but integration. The speed of light stops being a topic and becomes a background truth, like gravity beneath your feet or time behind every thought. When people first learn about relativity, it often feels like reality has been destabilized. Time slows. Space shrinks. Simultaneity disappears. The universe no longer behaves the way it should. But with distance, another interpretation becomes possible. Reality was never broken. Our expectations were simply too small. The speed of light did not complicate the universe. It revealed the rules that were already there. It tells us that the universe values consistency over convenience. That it would rather be strange than self-contradictory. That it would rather delay than collapse into paradox. This is not a universe designed to please intuition. It is a universe designed to hold together. And it succeeds. Across billions of years and unimaginable distances, the same constant applies. The same limit governs particles in accelerators and galaxies at the edge of visibility. Nothing gets special treatment. Nothing cuts ahead. The universe runs on a rule that is firm, impartial, and universal. There is something quietly ethical about that. No observer is privileged. No reference frame is absolute. Every perspective matters, but none dominates. Reality is not owned by the fastest, the closest, or the most powerful. It is shared, translated, and constrained equally for all. Even now, as you finish hearing this story, the light carrying these words took time to reach your eyes. That delay did not diminish the message. It made it possible. Without ordered signals, without causality, without the quiet discipline enforced by light's finite speed, meaning itself could not survive. So the speed of light does not stand in opposition to understanding. It stands guard over it. It ensures that when something happens, it happens somewhere, sometime, and in an order that can be followed. It ensures that memory can form, that prediction can work, that explanation can exist. It ensures that the universe can be known, not all at once, not instantly, but truthfully. And perhaps that is the most human lesson hidden inside this cosmic constant. Understanding is not about immediacy. Wisdom is not about speed. Depth is not about removing limits. The universe does not reveal itself instantly because instant revelation would be meaningless. It reveals itself gradually, carried by light, shaped by distance, filtered through time. And we, limited as we are still capable of understanding it. Not because we outrun its rules, but because we learn to think within them. The speed of light does not end curiosity. It gives curiosity a structure. It is not a barrier to truth. It is the reason truth arrives at all. And in that sense, the speed of light does not break our reality. It makes reality possible. To close this journey, it helps to return to the simplest image. We began with a flash of light crossing empty space. What once seemed instantaneous now feels almost ceremonial. That flash carries with it not just energy, but order. It carries the universe's insistence that events unfold, that causes travel, that understanding arrives only after waiting. In this final reflection, the speed of light stops being something we analyze and becomes something we live with. Every scientific revolution eventually reaches this stage. At first, a discovery feels disruptive. It overturns assumptions, rewrites rules, and leaves confusion in its wake. But with time, the disruption settles into clarity. What once felt like a crack in reality becomes a window into its structure. The speed of light followed this path. It began as a nuisance in experiments, became a paradox in theory, and ended as a cornerstone of meaning. We now know that the universe is not built on simultaneity, but on connection. Not on instant presence, but on delayed influence. Not on absolutes, but on relationships. The speed of light is the mechanism that enforces all three. This has an unexpected consequence for how we think about the future. Progress does not mean escaping the universe's limits. It means aligning with them more precisely. Every advance in physics has come not from ignoring the speed of light, but from taking it seriously. Every breakthrough has respected the rule rather than trying to cheat it. In that way, the speed of light becomes a model for understanding itself. Insight does not arrive instantly. It propagates. It requires distance from old ideas, time to cross uncertainty, and patience to be received clearly. Understanding, like light, has a finite speed. And that may be the most fitting parallel of all. The universe is not withholding truth from us. It is delivering it at the only rate that preserves coherence. Fast enough to allow change. Slow enough to preserve order. Exact enough to hold everything together. So when we say that the speed of light breaks our reality, what we really mean is that it breaks our illusions, about immediacy, about centrality, about control. What remains after those illusions fall is not emptiness, but structure. A universe that can be understood, even if it can never be mastered. Light does not rush. Reality does not rush. They arrive together, exactly when they are allowed to arrive. And within that arrival, delayed, ordered, and precise, everything meaningful finds its place. And so the journey ends not with a final answer, but with a settled understanding. The speed of light does not resolve every mystery. It does not tell us why the universe exists, or why there is something rather than nothing. What it does is far more subtle and far more powerful. It tells us how a universe can exist without tearing itself apart. It tells us that reality is stitched together by limits. That coherence requires patience. That order demands boundaries. Without those boundaries, nothing could persist long enough to matter. Every law of physics we trust depends, directly or indirectly, on the speed of light. Every reliable prediction, every stable structure, every consistent explanation leans on the fact that information does not arrive too early and does not arrive too late. It arrives when it is allowed to. This is why the universe feels dependable even when it is strange. You may not know what will happen next, but you can trust that whatever does happen will not violate causality. You can trust that effects will follow causes. You can trust that time will not unravel beneath your feet. That trust is earned by the speed of light. It is easy to forget how extraordinary that is. We live inside the rules so completely that it becomes invisible. Only when we push against it, when we imagine faster-than-light travel, instant communication, or absolute simultaneity, do we notice how much work that single constant has been doing all along. It has been holding time together. It has been keeping perspectives compatible. It has been preventing paradox from overwhelming possibility. The speed of light is the quiet custodian of reality. And perhaps the most profound part is this: the universe did not have to be this way. There is no logical necessity that reality must have a maximum speed. But the universe we inhabit does. And because it does, it becomes a place where history can unfold, where meaning can accumulate, and where understanding can grow. That growth is slow. It respects delay. It mirrors the universe itself. We learn the universe the same way the universe reveals itself, gradually. Through signals that take time to arrive, constrained by limits that cannot be rushed. In that symmetry, there is something deeply fitting. We are not outsiders trying to decode reality. We are participants shaped by the same rules we study. The speed of light governs our instruments, our theories, our perceptions, and even our thoughts. It is not just a fact about the cosmos. It is a condition of experience. So when all is said and done, the speed of light leaves us with a final, steady truth. Reality is not fragile. It is disciplined. It does not need to be instantaneous to be complete. It needs only to be consistent. And consistency, across time, across space, across every frame of reference, is exactly what the speed of light provides. That is how it breaks our old picture of reality. And that is how it makes a deeper one possible. There is nothing left to add in the sense of new facts, only one last way of seeing everything. That has already been said. The speed of light teaches us that reality is not built for shortcuts. It is built for continuity. Every event is connected to another by a path that must be traveled. Nothing simply appears everywhere at once. Nothing escapes the requirement to move, to propagate, to arrive. That requirement is what makes the universe feel real rather than dreamlike. In dreams, scenes shift instantly. Causes blur into effects. Time jumps without explanation. But the waking universe resists that instability. It insists on sequence. It insists on distance. It insists that information earn its arrival. The speed of light is the rule that enforces that insistence. Because of it, the universe has texture. Moments have before and after. Places have here and there. Knowledge has waiting built into it. And waiting, paradoxically, is what makes understanding durable. If everything were immediate, nothing would be meaningful. Meaning requires separation, delay, and connection across time. A cause must precede its effect. A signal must cross space. A truth must arrive from somewhere. Light provides all three. So when we say the speed of light limits us, we are only seeing half the picture. It limits chaos. It limits contradiction. It limits the collapse of order. What it gives us in return is a universe that can be explored piece by piece, moment by moment, without ever breaking its own rules. We cannot stand outside spacetime and see everything at once. But we can stand inside it and understand how it works. That trade is not a loss. It is the reason understanding is possible at all. In the end, the speed of light is not a wall at the edge of reality. It is the rhythm at its core. A rhythm that keeps time flowing, space coherent, and causality intact. A rhythm that allows the universe to tell a story instead of existing as a frozen whole. And we are part of that story. Every observation you make, every signal you receive, every insight you gain, arrives at exactly the speed the universe allows. Not too fast. Not too slow. Just fast enough for reality to remain itself. And with that rhythm in mind, the universe begins to feel less like a machine and more like a process, one that unfolds with discipline rather than haste. The speed of light is the tempo of that unfolding. It is the beat that everything else keeps time to, whether we notice it or not. We often ask what the universe is made of: particles, fields, energy, space-time. But just as important is how the universe behaves. It behaves patiently. It behaves locally. It behaves in a way that never allows information to appear without a path, or effects without causes. The speed of light is the rule that enforces this behavior everywhere, without exception. This means that the universe is not a place where anything can happen anywhere at any time. It is a place where what happens must travel. Where influence must move. Where understanding must arrive. And because of that, the universe can be trusted. Trust is not a word often used in physics, but it belongs here. We trust that experiments done today will mean the same thing tomorrow. We trust that signals sent will not arrive before they are sent. We trust that time will not loop unpredictably, and that reality will not contradict itself from one moment to the next. That trust exists because the speed of light exists. Even the most exotic ideas in modern physics, wormholes, quantum fields, curved spacetime, are built with this trust as a foundation. They may stretch reality to its limits, but they do not abandon its discipline. Every viable theory respects the same constraint: causality is sacred. This is why the speed of light feels less like a technical detail and more like a principle. It is not just a speed limit in the way a road sign is a speed limit. It is a condition for coherence. Remove it, and the concept of before and after dissolves. Remove it, and explanation itself loses meaning. So the universe does not allow faster-than-light shortcuts, not because it is cruel or restrictive, but because shortcuts would destroy the very structure that makes a universe possible. In this light, the speed of light becomes something almost philosophical. It is the universe saying that truth must travel, that knowledge must be earned through time and distance, and that reality cannot be collapsed into a single instant without losing itself. And perhaps that is why, after all the equations and experiments, the idea stays with us. It reaches beyond physics and into how we think about existence. About patience. About limits. About the difference between immediacy and meaning. We do not live in a universe that gives us everything at once. We live in a universe that gives us everything in order. And that order, quiet, relentless, and universal, is set by the speed of light. Nothing more needs to be added. Nothing needs to be rushed. The universe will continue unfolding, signal by signal, moment by moment, exactly as it always has. At the speed of light. And so, the continuation is not a new chapter, but a final settling, like dust after a long journey through space. Once you truly internalize the speed of light, you stop asking when reality will finally reveal itself all at once. You realize it never will. And more importantly, you realize it shouldn't. Reality is not designed to be consumed in a single instant. It is designed to be approached, step by step, signal by signal. The universe does not rush toward understanding, because rushing would undo the very structure that makes understanding possible. Every horizon you encounter, whether it is the edge of the observable universe, the boundary of a black hole, or the limit of what can be known, is not a flaw in reality. It is a consequence of the same rule that keeps reality from collapsing into contradiction. The speed of light draws these horizons with perfect consistency. This means there will always be questions that feel just out of reach. Not because we are insufficiently clever, but because the universe insists on order over completeness. It prefers coherence to total accessibility. And that preference is what allows anything to persist long enough to be studied at all. The universe could have been chaotic. It could have allowed influence without delay. It could have let effects outrun causes. But it did not. Instead, it chose a single, unwavering constraint, and built everything else around it. Stars burn in sequence. Galaxies evolve in time. Life emerges slowly, shaped by patience rather than immediacy. The same rule that governs photons also governs history. And when you look at it this way, the speed of light stops feeling like an obstacle to human ambition. It becomes the reason ambition has meaning. Goals require time. Journeys require distance. Growth requires order. A universe without delay would leave no room for any of these. Even curiosity itself depends on not knowing everything at once. So the final understanding is not frustration, but alignment. We are aligned with a universe that reveals itself gradually. We are aligned with a cosmos that values consistency over convenience. We are aligned with a reality that does not bend to desire, but rewards understanding. The speed of light is not something we must overcome. It is something we must accept in order to see clearly. And once that acceptance settles in, a strange calm follows. You stop asking how to escape the universe's limits. You start asking how much can be understood within them. That question has no end, and that is precisely the point. Because as long as light continues to travel, as long as signals continue to arrive, as long as cause continues to precede effect, the universe will keep offering itself to be known. Not instantly. Not completely. But truthfully. At the speed of light. And with that truthfulness comes the final, quiet reconciliation. The universe is not hiding from us. It is simply speaking at a pace that preserves meaning. The speed of light is that pace. It is the universe's way of ensuring that revelation does not become noise, that existence does not collapse into simultaneity, and that understanding remains something that unfolds rather than overwhelms. We often imagine that to know everything would be to stand outside time and space, seeing all events at once. But the speed of light teaches us why that image is misguided. To see everything at once would be to erase sequence. To erase sequence would be to erase explanation. And without explanation, knowledge loses its form. Instead, the universe offers something subtler and far more robust. It offers knowability without omniscience. It offers order without immediacy. It offers truth that arrives, not truth that floods. This is why science progresses the way it does. Not in leaps that violate the universe's limits, but in refinements that respect them. Each discovery waits for signals to arrive, waits for data to propagate, waits for understanding to catch up. The structure of knowledge mirrors the structure of reality because both are governed by the same constraint. The speed of light does not just shape physics. It shapes epistemology. It defines what it means to learn, to test, to confirm. It is the reason evidence must travel, experiments must be repeated, and conclusions must be consistent across observers. And this consistency is the final gift. No matter where you are in the universe, no matter how fast you are moving, no matter how strong the gravity around you is, the rule remains the same. Light will not cheat. Information will not arrive early. Reality will not contradict itself. That reliability is what allows meaning to survive scale. It is what allows the same laws to govern atoms and galaxies, moments and eons. It is what allows us, small, slow, and local, to understand a universe that is vast, fast, and ancient. So the story does not end with a breakthrough or a revelation. It ends with a recognition. The speed of light is not something to overcome. It is something to stand within. It is the framework that makes discovery possible, patience meaningful, and reality coherent. As long as light continues to travel, the universe will Continue to be understandable, never all at once, never without limits, but always without contradiction. And that is enough. Because a universe that can be understood, even partially, is a universe worth exploring. One signal at a time. And in that continued exploration, something quietly profound becomes clear: the speed of light does not merely regulate the universe, it teaches us how to live within one. We often treat limits as problems to be solved, walls to be broken, barriers to be bypassed. But the universe, through the speed of light, offers a different philosophy. It shows that limits can be generative, that boundaries can create structure, that restraint can be the foundation of richness rather than its enemy. Because light is finite, distance matters. Because distance matters, journey matters. Because journey matters, experience gains depth. A message sent across space carries weight precisely because it must travel. A discovery feels meaningful because it arrives after effort, patience, and time. Even memory owes its coherence to the fact that the past cannot instantly overwrite the present. The speed of light ensures that the universe has thickness, layers of time stacked gently upon one another. It ensures that moments do not collapse into each other, that history does not flatten into immediacy. Without this thickness, there would be no narrative, no growth, no becoming. In this sense, the universe is not optimized for speed. It is optimized for continuity. This continuity is what allows complexity to emerge. Stars do not ignite and extinguish instantly. Galaxies do not form in flashes. Life does not appear fully formed. Everything unfolds through sequences that respect causal order. The speed of light is the unseen conductor keeping that order intact. Even our deepest longings, to explore, to understand, to connect, are shaped by this rule. We long to reach the stars precisely because they are distant. We value communication because it crosses space. We treasure understanding because it takes time. A universe without delay would be a universe without longing. A universe without longing would be a universe without meaning. So the speed of light does not diminish wonder. It makes wonder possible. And perhaps this is the final reconciliation. The universe does not promise us immediacy, omniscience, or control. What it offers instead is coherence. A reality that can be trusted to behave the same way everywhere. A reality that unfolds without contradiction. A reality that allows understanding to grow rather than shatter. We are not meant to outrun light. We are meant to follow it. To observe where it has been. To infer what it reveals. To accept what it cannot bring us yet, or ever. In doing so, we align ourselves with the deepest structure of reality. Not as masters of it, but as participants within it. The speed of light does not close the universe to us. It opens it, carefully, consistently, and honestly. One arrival at a time, and following that alignment, a final clarity settles in, one that feels less like a conclusion, and more like a stable viewpoint from which everything else makes sense. The universe is not withholding speed from us. It is offering sequence. It is offering a way for things to matter in relation to one another. The speed of light is the rule that makes relationship possible without confusion. It allows events to be connected without collapsing into each other. It allows difference without disorder. Because light takes time, the universe has perspective. Perspective is what allows contrast. Near and far. Before and after. Here and there. Without perspective, reality would be flat. With it, reality gains dimension, not just spatial, but experiential. This is why the universe can be vast without being meaningless. Distance does not dilute significance, it deepens it. When light reaches us from a galaxy billions of years away, it brings not only information, but context. It tells us where we stand in a story far larger than ourselves. And yet, that same rule keeps us grounded. It prevents us from pretending we are outside the story. We cannot jump ahead. We cannot see the ending. We receive the universe at the same pace it allows everyone else. This equality is easy to overlook, but it is profound. No matter how advanced a civilization becomes, no matter how powerful its technology, it cannot rewrite the order of causality. It cannot force the universe to speak faster than it does. Knowledge may deepen, reach may expand, but the rule remains. In this way, the speed of light is the universe's final arbiter. It decides when influence arrives. It decides what can be known together and what must remain separate. It decides how reality stays consistent across unimaginable scales. And consistency is the quiet miracle here. A universe this large could easily be incoherent. Laws could shift from place to place. Causes could unravel. Time could lose its direction. The speed of light prevents all of that, not by force, but by structure. It is the thread that keeps the fabric from tearing. So the longer we sit with this idea, the more it stops feeling restrictive and starts feeling protective. The universe is not fragile because it is slow. It is stable because it is slow enough. Slow enough for stars to form. Slow enough for planets to cool. Slow enough for life to reflect on itself. A universe that rushed would leave nothing behind. And so, when the question finally fades, when we stop asking how fast light travels and start asking what that speed allows, the answer becomes clear. It allows reality to remain reality. It allows history to exist. It allows understanding to accumulate. The speed of light is not a limit placed on us. It is the condition that allows us to be here at all. And at this point, there is nothing left to prove. The equations have done their work. The experiments have spoken. What remains is not new information, but understanding. The speed of light is not a number to memorize. It is a reminder. A reminder that the universe does not operate in a hurry. That reality does not allow everything to happen at once. That meaning only exists when there is order, distance, and time to wait. We once believed time was absolute. Light shattered that belief. We once believed space was fixed. Light bent it. We once believed, now, belonged to everyone. Light showed us there is no single, shared present. But in breaking these assumptions, light did not destroy reality. It revealed a deeper structure. Beneath it, one more precise, more consistent, and more resilient than anything intuition ever offered us. Because of the speed of light, causes cannot arrive after their effects. Because of the speed of light, memory cannot be scrambled. Because of the speed of light, the universe does not contradict itself. There are no shortcuts. No special privileges. No ultimate point of view. Only different perspectives, all bound by the same unbreakable rule. Light favors no one. It does not care whether you are a particle, a planet, or a person. Its law applies equally, quietly. Impartially, absolutely. And that is precisely why this universe can be understood. We do not stand outside reality observing it from above. We exist inside it, constrained by the very limits we seek to comprehend. That is not a weakness. It is what makes understanding honest. We cannot see everything at once. But we can understand why that is impossible. And understanding our limits is a deeper kind of knowledge than any illusion of omniscience. In the end, the speed of light does not break reality. It breaks our naive expectations of it. And in return, it gives us something far more valuable. A universe with order, with depth, with history. A universe that can be understood, one step at a time. Not faster. Not slower. Exactly at the speed reality needs to remain itself.